Okay, so now for example 8 is a little more difficult than example 7, and that is because we don't have one reactant, we have two. So there are some things that we have to consider when dealing with a two reactant problem, or two or more reactants. So we're going to start by writing the expression rate equals K. Remember, we only include the reactants in our expression. We're going to call this is a C. We're going to call that to the m power, and we're going to say OH negative 1 to the n. We could do xy, any kind of letter you want to use for your exponents. So we're going to figure out the order of m and the value of the n, and then we have the orders, and then we can do some things to figure out what K is and the rate and how the concentration changes over time. Now, because we have two reactants, or two or more, we can't just randomly pick. We actually have to look and see when are each experiment's constant, because we've got to pick each reactant's experiments using the rate over rate equals concentration over concentration based when the other reactant is held constant. Let me say that again. For reactant A, if I can call this reactant A, all right, we're going to call this reactant A for a moment, and this is reactant B, I have to pick the experiments for A where B is held constant, and I have to pick for B where A is held constant. So we need to examine our data here and look and see when things are the same. Now, I've noticed that this table goes the same way example 7 went. I have tried over the years different ways, and here's what I find to be the easiest way to tackle this. So thinking about this reactant, where is it constant? Meaning it has the same data, same concentration, because that's what this is. This is concentration, this is concentration. So I'm looking where concentration is constant. And this is what we will do in an experiment, or what you would do in an experiment. So I see that experiment 2, 4, and 5 for this reactant are constant, nowhere else, meaning experiment 2, 4, and 5 all have the same concentration for that reactant and nowhere else. Now you could have two sets, but in this case we didn't for the first reactant. For hydroxide reactant, I see that it's constant with respect to experiments 1, 2, and 3. 1, 2, and 3. Now this is the rate down here, so we don't care. We're not worried about where it's constant with that. We wouldn't actually even look at that because that's going to be not needed for this piece. In terms of, we picked reactant A where B is held constant. So this is reactant A. We're going to call this A just for simplicity. So I got to pick two experiments for this reactant to use where B is held constant. I like to split my screen or my paper into each. So I'm going to say, I'm going to think about, I'm looking at this first, this reactant first, and then this is going to be my other reactant. So we're going to apply that expression, rate 2 over rate 1 equals concentration 2 over concentration 1 to the power, for each of these. But to pick which experiment sets I use for this one, I don't use this one, I look at hydroxides. Okay, so we see that hydroxide, OH minus, is constant with respect to experiments 1, 2, and 3. So I could do several options here. I could put 2 over 1, or I could put 3 over 1, or I could put 3 over 2, or I can flip these all and say 1 over 2, 1 over 3, 2 over 3. I like to put the larger number on top. It usually gives us non-negatives, not always, but most often it does. Okay, so we're going to do 3 over 2. So we're going to talk about the fact that we're going to say rate 3 over rate 2, and I just picked that at random. You could pick a different one and you should get very close to the same order. Concentration 3 over concentration 2 to the power of m. So notice I have rate 3, concentration 3, rate 2, concentration 2, meaning that the rate and the concentration have to be the same as you go from left to the right of the equal sign. So we're going to look for rate for experiment 3. Now, remember, we're solving for what I called A, right? So CH3, 3, CBr. So we use the information for A for right here in its concentration. That was never a very good mouse flow there, so we're using that. Okay? Whatever concentration you solve for, you're going to use the data for that concentration. So let me be clear. We pick which experiment sets based on when the other one's held constant. So let's do that again on this side, and then I can go through that again. So because this one is OH minus, I don't pick which experiment sets to pick OH minus for using the OH. I look and see when is the other reactant constant. So it's constant with respect to 2, 4, and 5. So let's do 4 over 2. Because we could do 4 over 2, we could do 5 over 2, and we could do 5 over 4. We could pick any of these sets and then flip them also. So we could actually have 6 different ways we could set this up. We should all get the same order. So let's pick 4 over 2. So we're going to say rate 4 over rate 2 equals concentration 4 over concentration 2, all raised to the n power. And you could use m again if you want it, but I just think it helps to keep it separate. Notice I have rate 4 concentration 4, rate 2 concentration 2. Now, let's go over that one more time because this can be very confusing. Because we have 2 or more reactants, we cannot just randomly pick like we did for experiment 1. We have to actually pick for each reactant when the other reactant or reactants is held constant. So that's why we did this first. I looked here and I found that with respect to this first reactant, I see that it is held constant with respect to experiments 2, 1, excuse me, let me try that again. 2, 4, and 5. That's why I wrote 2, 4, 5 there. The other reactant is held constant with respect to 1, 2, and 3, meaning one of the values is the same for the concentration. So then, for this reactant, I don't pick any. I have to pick when the other reactant held constant. That's why I'm making my list. So for a reactant, I called this A, and we called this B, just for simplicity and looking, right? We know that A has to look at B, and B is held constant with 1, 2, and 3, so we could have picked any of these. This is what I picked for us today. And with B, we look at the other reactant, see when it's held constant. We see it's held constant with experiments 2, 4, and 5, so I picked 4 and 2. Okay, so now we're going to apply this formula twice to our problems here. I'm going to go down some just so we can see my math. Okay, so we're going to do rate 3. Now remember, rate's down here at the very bottom. Rate 3, so this case 0.015 over rate 2, 0.010 equals concentration 3. Now concentration 3 of who? Of the reactant we're solving for. So this will be 1.5 over concentration. I may have not said, I don't know if I just said 2 or 3, but I was following this. Concentration 3, which was 1.5, over concentration 2, which is 1.0. Now remember, I'm using the concentration for the reactant I'm solving for. That's why I'm looking at these two numbers to the m power. Now we're going to figure out what these values are. So 0.15 divided by 0.10, and we get 1.5 here, 1.5, and of course this will be 1.5 to the m. We're going to take the natural log of both sides, and you need to show at least this much here. And then you may already see that because they're going to be the same, it's going to be the ln of this equals 1.5. Oops. Let me try that differently. We forgot to do the ln of that first. I forgot to write that first. The ln of 1.5 to the m. And just for purposes of showing you that it'll work out okay, I'm going to go ahead and plug it into my calculator, although I think most of you see that that's going to, already can probably see what that's going to give us. 0.41, and then this is going to be 0.41 to the m, so the m is going to be, it's going to be first order. All right, we're going to apply the same math over here, except for we got to get a different set of data. So we're going to look again, and remember, because we're solving for OH, we don't pick OH stuff. We had to look for the other reactant to see which set we pick. Once we pick our set, then we will focus on OH concentration. So when I do concentration, it has to be every time that concentration must be of whatever we're solving for. Just like over here, this was the concentration of that reactant. We pick based on the other, and then we plug in data once we know what sets that we can pick. Because we must pick based on when the other reactant or reactants are held constant. So now we're going to look at rate 4, which is right here, over rate 2, which is right here, equals concentration of 4 for who? This one that we're solving for. So that's going to be 0.10 over concentration 2, 0.050, all raised to the n power. Double checking my numbers here. Okay, those look good. So now we're going to take the ln of 1.0, and then, actually, let me do this the way I've been doing it to be consistent. So we're first going to divide, and we get 1.0 here. And then we're going to take and figure out what that is. And that is 2.0 to the n power. And now we're going to take the ln of both sides. Now, I will talk to you about in just a moment about the minimal amount of work you must show to get credit for these problems. So the ln of 1.0 equals the ln of 2.0 to the n. This is ln. Okay, and so then we're going to take the ln of 1 which is 0. And then we'll take the ln of 2, which is 0.69. And then this n comes down, but we know that n is going to be a 0. Okay, so before I tell you what you have to have as minimal, I'm going to go ahead and finish this up. Now we know the order for each reactant, so now we can go up here and we can write a proper expression. So we would write, and what we do is we'd say, okay, we know this is first order because this came out to be a 1 down here. And this is 0 order, right? So now we know anything to the 0 power is 1, so then we know that the final expression would be rate equals K, CH3, 3CBr raised to the first power, and you wouldn't write the 1. So this would be our final rate expression for this problem. Now I told you I would talk to you about what I expect to see. I expect to see you set the generic formula up like this, so this must be shown in each case to get credit. I expect to see the numbers plugged in, and I expect to see as much of the math. The more the math you show me, the more partial credit I can give you, especially if it's an assessment. So I expect to see at a minimum the generic expression with the numbers plugged in, and then the value of the exponent. The more you show between this piece here and the m or n answer, the more partial credit I can give you, or at least, if nothing else, the more I can help you find your mistakes. So it's very important that you try to show as much of your work as possible. Again, must see this, must see the numbers plugged in, and must get the m answer. Okay, I prefer you to show as much of this as possible if you want me to be able to help you and or give you more partial credit when that's possible. Reach out if you need some help.